Welcome to a new arc, the Recurrence, where the past is just a preview, only on your dose of Wowness.
Somewhere in the fossil record, buried under 250 million years of rock, there is a rhythm. Not a heartbeat you can hear, but one you can track if you step back far enough to see the sheer volume of species dying off over time. Look at this graph showing major mass extinction events. When paleontologists mapped out these planetary die-offs, they found they weren't randomly scattered. They cluster at distinct, even intervals. Roughly every 26 million years, something comes through and thins the herd. 26 million years is an incredibly specific number. Earthly chaos doesn't keep a schedule like that. Asteroid impacts, volcanic eruptions, collapsing sea levels, these are isolated disasters, not clockwork. If a mass extinction arrives exactly on a metronome, the mechanism driving it cannot be random earthly bad luck. It has to be an external schedule, something completely disconnected from the planet itself. Until the early 1980s, paleontology treated extinctions as singular events. You find the dead species, check the rock layer, and look for a local culprit. Nobody was looking for an overarching, repeating frequency. That changed when Sepkoski built a massive database, mapping thousands of marine families, tracking exactly when they appeared and when they vanished across eons. He created a continuous curve of life and death that covered 250 million years. His colleague, David Raup, applied a mathematical tool called periodogram analysis to that data. It's a technique normally used by physicists and economists to find hidden repeating signals inside noisy data, like sunspot cycles. When they ran the numbers on 12 distinct extinction pulses, the famous Cretaceous-Paleogene event, the one that wiped out the non-avian dinosaurs, was just a single data point on the curve. It held no special weight. By treating all that death as a continuous wave, Raup and Sepkoski found a repeating signal that was so mathematically stubborn, it forced scientists to look up from the rocks and out into the solar system to explain it. Within 12 months of the data going public in 1984, two entirely separate teams of astrophysicists looked at the exact same 26 million year anomaly and proposed nearly identical solutions. The Nemesis hypothesis suggested the Sun has a hidden companion star locked in a massive orbit. Every 26 million years, it grazes the Oort cloud, sending a shower of comets hurtling toward the inner planets, increasing the odds of an impact. The second team proposed a 10th planet doing similar gravitational work closer to home, the Planet X hypothesis. Neither team actually had physical evidence of these objects. The mathematical gap in the fossil record was so glaring that they had to invent an invisible culprit to fill it. If a planetary heartbeat sounds like the mystery you want in your feed, this is a good moment to subscribe. This is day 131 of your dose of Wowness, and we have 9 more recurring patterns still to come in this arc. These theories proposed a direct mechanical link between the deep space orbital dynamics of the Milky Way and the biological survival of life on Earth. The sky was literally setting the timetable for the ground. The pushback was fierce. Paleontologists pointed out that dating these compressed layers of ancient rock is an inherently fuzzy science, especially with 1984-era technology. The error bars on those dates can stretch for several million years in either direction. When you are relying on dates that imprecise, building a perfectly regular 26 million year metronome is a mathematically fragile exercise. Statisticians introduced the multiple comparisons problem. Take any set of noisy data, search it aggressively for a frequency, and math will hallucinate a pattern. The terror of a cosmic clock suddenly faced a very grounded reality. It was entirely possible that this extinction schedule was a statistical illusion, built by carefully rearranging messy, poorly dated rocks. To settle the debate, astronomers realized they just had to look for the clockmaker. Even a very dim brown dwarf companion star like Nemesis would emit detectable heat in the form of infrared radiation. So in the early 2010s, NASA launched the WISE mission, a space telescope specifically designed to scan the entire sky and detect exactly those faint heat signatures. This sweeping infrared map of the sky allowed astronomers to look deep into the outer edges of the solar system, capturing objects far too dim for standard optical telescopes to see. When the survey was complete, the result was a clean, undeniable negative. The WISE telescope ruled out any companion star matching the size or distance the Nemesis hypothesis required. Astronomy provided a definitive answer. The prime suspect was dead. There is no hidden companion star orbiting our sun. But disproving the star didn't erase the pattern that prompted the search. A confirmed mechanism is completely separate from the raw fossil data itself. 4 decades after Raup and Sepkoski published their paper, scientists using modern, highly precise rock dating are still split. Some recent analyses find the 26 million-year signal stronger than ever. Others correct for the dating errors and watch the pattern dissolve into random noise. And alternative clocks remain on the table. Some researchers suggest our entire solar system slowly bobs up and down through the dense plane of the Milky Way, exposing Earth to higher cosmic risks on a massive, recurring schedule. The data keeps returning a signal, and our tools keep failing to find the cause. That gap between a pattern we can measure and a mechanism we can't explain isn't a failure of science. It is exactly where the frontier of human knowledge sits today. Tomorrow, for day 132, we stay within the theme of recurrence, but we trade the sky for the ground. The Volcano's Return looks at supervolcanoes that don't just erupt once, but keep coming back on their own long, terrifying schedule, including the one sitting under Yellowstone right now.